All right, let's start on the first derivative test, and we're going to make some observations. Basic concepts are these. If the derivative of x is less than 0, then that graph has tangent slopes, which are downhill tangent slopes, which means the graph itself is what's called decreasing. It falls from left to right. The opposite is also true. For any values of x, which the derivative is positive, that means the tangent slopes have an uphill slope from left to right. In this particular case, this is called increasing. Y values rising from left to right, increasing. It means the derivative is greater than 0. Y values falling from the left to right, decreasing. It means the derivative values are less than 0 or negative. Okay? So let's talk about what happens when the tangent lines are horizontal. Okay? If I set a derivative equal to 0, I get what's called critical points. Chances are pretty good that these are either minimums or maximums. All right? If that critical y value, we're going to find x values, but if its y value is lower than the y values all around it, it's a minimum. And if the y value is higher than the y values immediately next to its left and right, it's called a maximum. Let's see if you can figure this out. So if you need to stop the video here for a moment. But here's some basic concepts. I've given you values of f prime of x, and I've given you x values. Can you sketch the curve, sketch a basic shape of this graph based on what you see here? Notice that f prime of x is positive on the interval here, f prime of x is positive on the interval here, f prime of x is negative on the interval between the two zeros, and f prime of x is equal to 0 at 0 and 2. Okay? Graph should look something like this. Again, to the left of 0, it should be increasing. At 0, it should horizontal. Between 0 and 2, it should be decreasing. And to the right of 0, it should be positive. Again, this positive derivatives, positive slopes, increasing. Negative derivatives, negative slopes, decreasing. 0 derivatives, 0 or horizontal slopes, chances are these are turning points. Moving on to the second derivative test. Basic concept with the second derivative. Again, remember that the second derivative is just the derivative of the first derivative. Okay? In this particular case, notice this is what we call concave up. If all tangent slopes lie below the curve, okay, this is where f double prime of x is positive. If double prime of x is positive, that means the graph is concave up. Notice I'm dealing with a parabola here, and of any parabola, x squared, for example, if I take the first derivative, it's 2x, and if I take the second derivative, it's just the constant 2. Constant 2, always positive. You will see that always positive means upward turning, in this case, concave up. A little bit different of a problem, if we'll take a look at y equals rad x looks something like this. Notice that the tangent lines are always sitting on top of this particular curve. This curve is what we call concave down. If we actually solve for the double derivative, we'd find that the double derivative is negative 1/4 over x to the negative, over the square root of x to the third power. All right? Please understand this domain. If you want to talk domains for a minute, you can't have negatives underneath the radical. So literally the domain is all positive numbers. And anytime you plug in a positive value of x here, this double derivative will be negative, means concave down. Tangent slopes are above. So how would we use this information? Well, let's look at this degree 3 equation. And first of all, we'll define the critical points by setting the derivative equal to 0. So we take the derivative using the power rule. We set it equal to 0. We factor. We find out that if x plus 4 times quantity x minus 2 is 0, it must be the case that either x is negative 4 or x is positive 2. These are what we call critical values. They're possible mins or maxes. So one way to check them out also, we'll do this in a second. If we did the first derivative test, I'll show you that, but I'll also show you second derivative test. Second derivative test says, if I take the second derivative and I set it equal to 0, I get what's called point of inflection. Those are what's called changes in concavity. So a thing that's concave up changes to concave down. That usually happens at a point of inflection. In this case, it's x is negative 1. Again, the value that makes the double derivative equal to 0. looking at the second derivative test, if we plug critical points into the second derivative, so I'm going to take -4, plug it into the second derivative, which is 2x plus 2. 2 times -4 plus 2 is a negative number. This is concave down. Must mean that critical value at 4 must, or -4, must have been a max if it's concave down. By the same token, if I plug in 2, the other possible critical value that made the first derivative equal to 0, if I plug that into the second derivative, again 2x plus 2, I get 6, in this case concave up, which means whatever critical point I found must have been a min. So that's the idea of the second derivative test. If the value which is critical makes the second derivative negative, it's a max. If the value which is critical makes the second derivative positive, it's a min because of concavity. That's what I got. Thanks.